Okay, so here we have a next structure to consider. So this one is the electric field due to a charged disk. Okay, so the previous one is a charged ring. Okay, so yeah, it is somehow like in one-dimensional integration in one-dimensional. So this one will be integrated in 2 dimensions. Okay, so here we have a charged disk. So a disk of radius r and uniform positive charge. Okay, so the ring shown has radius r and radial with width dr. So it set up a differential electric field dE at point P on its central axis. So actually when we try to calculate this charge disk, okay, we will try to calculate the E field generated by this charge disk. If we don't make use of the previous knowledge, that is the E field generated by this, the E field generated by this charge ring. Okay, so actually we would like to consider something like we will try to separate this disk into, let's say, cut it in the x-axis, cut it in the y-axis, something like this. Okay, something like this. So every small pieces we would like to calculate the dE, dE at point P or something like this. But it will be the calculation will be very difficult. Okay, so yeah, if we make use of the Cartesian coordinate. Okay, one better idea is to make use of the polar coordinate instead. Okay, so which means that we try to separate this. Okay, so using this concentric circle 同心圆去切，然后 and then we also cut it in different angle, something like this. Okay, so we will try to separate this circle into many small pieces. Of course, all the small pieces doesn't have the same area. In the previous case, we actually cut all the pieces into many rectangles, but actually we try to cut it into something like that. Okay, if we don't really make use of the previous knowledge, then we really need to do that, and then we integrating over the r-axis and also the theta axis. But hopefully, if we make use of the previous knowledge, we can consider this thing will be the E field generated by a ring. Okay, so we can also consider that we try to separate in this into many rings with different radius. Okay, with different radius. Of course, all this ring will have a small thickness. Okay, the thickness will be dr. OK， 就是我们把一个实心的圆盘，就把它分割成很多不同的圆环，它有一个就是很短的厚度了，就是有一个厚度 dr， 就是很小的无穷小哦。但是所有的环有不同的半径有不同半径的环组成一个圆盘。OK， 所以我们就可以用前面那个式子。OK， so it is like so we try to make use of this expression. Okay, which is the E field generated by a charged ring. Okay. And here we try to make things like so here we only have dq on this ring. Okay, so it turns out to be we change this E to be dE and change this Q to be dQ. Okay, and actually we also change this capital R to small r because the capital R is the radius of the disk, but every small ring we will consider the radius of every small ring to be small r. So here we use the small r instead of capital R. So that's the basic setup. We make use of the knowledge that the E field generated by a charge ring for this charge disk. Okay, and then we try to change the according variable. Okay, like this. Okay, and then we try to integrate this thing for R from 0 to capital R. But of course, we would like to do some change of variable. Okay, so this is the equation in the previous page, and then we want to sum, which means we want to integrate this thing from R equals 0 to capital R. So we would like to do some change of variables. Okay, so here dq will be something like sigma times dA. Okay, so just now for the linear charge density, we use the symbol lambda. Okay, the Greek letter lambda for the charge density. But here will be a surface density. Okay, so 这个是面积的电荷密度. Okay, so this sigma is the surface charge density, and the corresponding SI unit will be C over meter square, okay, instead of C over M. Okay, so here we have a sigma times the small area will be the charge on this area. Okay, so we consider this yellow ring has a area small dA. Okay, like this. And how to calculate the area of this ring? Okay, so here we consider this dr is very thin. Okay, this dr is very short. Okay, so you can try to consider something like you try to cut this ring out, and then you try to expand it, and then it become a rectangle. Something like this. Okay, so you try to cut it out, and then you try to expand it. Okay, so the height of this rectangle will be dr. Okay, which is the thickness of this ring. And then so the width of this rectangle will be the circumference of the circle. The circumference of the circle will be nothing but 2 pi small r. Okay, 2 pi small r times dr will be the area. The area here, dA will be the height multiplied by the width. So it will be 2 pi r dr, or something like this. Okay, so here dA will be 2 pi r dr. Okay, so here we have dr, so we can do the integration dr from 0 to capital R. Okay, so we can try to put this thing into here. Okay, so here we have dE, this is K. Okay, Z, we put it here, and then this term we also put it here. So this dQ becomes sigma, and then 2 pi r put in here, dr put in here. Okay, and then we can try to do some cancellation. Actually, we can cancel this pi with this pi, and we just put this thing in the front, sigma z in the front, and then over 4 epsilon naught in the front. So here we have 2r dr here, and then we also have this term here. Okay, so here we try to do the integration. A little bit more complicated, but not too difficult, hopefully. So here we have we have the total E generated by the whole disk, which is the integration of dE, and then we try to plug in this expression here. Okay, so here we have sigma z 4 epsilon naught 2r dr over this thing, and then we integrate this thing from 0 to capital R. And actually this part is independent to R, so we can just put it outside. So here, this is a function of small r, so we need to find its antiderivative. Okay, so we can do some change of variables, which is like 2r dr will be like dr square. Dr square will be 2r dr. So just take the derivative of r square will be 2r. Okay, something like this. And actually, z square is actually a constant to r square. So you can consider this thing is also this thing. Okay. You can, yeah, if you are not familiar with this kind of change of variable, you can consider something like dr square plus c square dr. Okay, so for the first term, take the derivative of r square will be 2r. And then z is a constant to r, so plus 0. Okay, and then you can just multiply this dr to the right side. Okay, so this thing is 2r dr. So 2r dr is actually this stuff. And the reason why we add it here is actually we have a z square plus r square here. Okay, so here we also have a c square plus r square. So that is like a polynomial, yeah, with a -3 over 2 power, -3 over 2 power. So the integration of this thing is like we add 1 to the power, so -3 over 2 plus 1 is -1/2, and then we divide -1/2 here. Okay, so finally, and then we also need to evaluate this function from 0 to r. Okay, and then with the negative sign, we can just flip it. Okay, so we evaluate from capital R to 0. Okay, which means that, okay, we can actually cancel this 2 with this 4 down to a 2. So in the front, we have a sigma z over 2 epsilon naught in the front. And then we try to evaluate this thing. Okay, so this negative sign already swap the order here. Okay, so in that case, we try to plug in z, which means r equals 0 and r equals capital R into this function, and then subtract them. Okay, so first we subtract r to here without the negative sign. So r equals 0, it becomes z squared to the -1/2 power. Okay, so it becomes 1 over z, and for the second term we minus r equals to capital R, and then also this thing to the -1/2 power, so it becomes 1 over square root of c squared plus capital R squared, like this. Okay, so finally we can distribute this z into here and here. So this z and z cancels, so the first term becomes 1. And then also here we have a z over this square root of c squared plus capital R squared. So the final expression look like this for this charge disk. So far, any questions? Yeah. Okay, so actually this is the expression, yeah, for the E field generated by a charge disk on this z-axis also. Yeah, if it is not on the z-axis, the expression will be even much more complicated. Okay, so here we have another condition, not the far field condition, but here we try to assume this disk is infinitely large. 就是无限大的一个盘子 ，OK， 所以它就是说你会说我怎么找到一个无限大的？但是 so the idea here is like if we make this assumption, the expression here will be extremely simplified. Okay, extremely simplified. And even though for the real world we can't find infinite disk, we will make use of this approximation. Okay, so the idea here is like if we assume that this capital R is infinitely large, so yeah, so this is one, nothing special. This is a constant, nothing special. So if we just looking at this term, if capital R is infinitely large, then okay, then we can really have something like you can consider it like z over r and then over z over capital R square plus 1 and then take the square root, something like this. Okay, so if R is infinitely large, so this term will be 0, this term will also be 0, so it becomes 0 over 1, okay, which is 0 if R tends to infinity, which means that R is much larger than Z. Okay, so in that case, if we assume R is infinitely large, the second term vanish. So the only remaining terms is sigma over 2 epsilon naught. 2 epsilon naught is a constant. You should still remember it is 8.85 times 10 to negative 12. This is also a constant if we don't change the charge of the disk. This is the surface charge density. So given a specific charge on this disk, this is a constant, which means that if we assume this disk is infinitely large, the E field generated by this disk is a constant. Okay, this is a constant. It is independent to Z. OK， 这个就是为什么要做这个假设的原因，就是如果我们假设这个 R 是无穷大，就是这个盘子是无穷大的话，那它所产生的 EV 它就跟距离无关，因为本来的话，如果这个是有限大的话，这个 expression 是跟 Z 有关的，所以就是越远的话应该会越小，越远的话会越小，越远的话这个 term 就会越接近1啊，那整个就会越接近0。那现在如果假设这个盘子很大的话，那这个电场就会是一个常数，它就会产生一个均匀的电场。Okay, so this is why we make this assumption. Although for the real world we cannot find an infinitely large charge disk, but we will make use of this approximation. 那我们用这个的意思是，到时候我们的盘子不是无限大，但是它会在一个相对比较局限的范围里面产生一个均匀的电场，我们是这么套用这个概念的。Okay, so here we discuss a point charge in an electric field. Okay, so here it says if a particle with charge Q is placed in an external electric field E and electrostatic force F acts on the particle. Okay, so it is nothing special. It is just the definition, something like the definition at the very beginning. So at the beginning of this chapter, we try to define E to be F over Q0. Okay, so here we just move this Q to the other side, so we have a F equals QE, nothing special. So it says the electrostatic force acting on a charged particle located at an external electric field E has a direction of E if the charge Q of the particle is positive. Okay, 所以正电荷的话就是那个力就跟电场同一个方向 and has the opposite direction if a Q is negative. Okay, so yeah, nothing special. Okay, so here it try to mention the mechanism of the inkjet printer, 就是那种喷墨的打印机啊，喷墨的。Okay, so yeah, so the idea is like suppose we have a color of the ink. Let's say this is a green color or other colors. Yeah, so let's say if we have a impact. Okay, so G. Okay, so it will inject some ink drop, okay, to the right side. And here we can try to add some charge on this ink, okay. And then here we have a parallel plate. Let's say this is a positive plate, and then we have a negative plate on the bottom, okay. So in this case, we will assume inside between these two parallel plates, it will generate a uniform E field pointing downward. Okay, we assume that we can generate a uniform E field pointing downward. Okay, so in that case, we try to control the charge amount adding on this ink, so that if we try to add more charges, then the force acting on the ink, when the ink goes through the parallel plate, okay, the force will be larger. The force will be larger. So yeah, and in such a way, we will try to add some negative charge, add some electron on the ink. So actually, for example, at this point, okay, so E is pointing downward and the charge is negative. So the force will be pointing upward, and yeah, all the way through is uniform E field, so the F is always pointing upward. 就是那就有点像那个抛射运动嘛，只是说这个力就往上的，就类似这个意思。Okay, so if the charge is larger, then the locus of the ink will bend more if we don't insert any ink insert any charge on the ink, then the ink will go straight on the paper. Okay, so that's the idea, how to control where to print a specific color. Okay, so it says drop short from generator G, receive a charge in the charging unit. Okay, this is the charging unit to add the charge on the ink, and then the input signal from a computer controls the charge, and thus the effect of the E field on where the drop lands on the paper. 就是它算好，就是加多少电荷，它就控制这点墨了，就是转到哪个位置。Okay, so here we have a sample problem. So it says the deflecting plate of an inkjet printer with a superimposed coordinate axis and ink drop with mass m and a negative charge of magnitude q enters the region between the plates. Initially moving along the x-axis with a speed vx, okay, 就是抛射运动了基本上。Okay, so the length L of each plate is 1.6 centimeter. Okay, so this is the length L, which is 1.6 centimeter. So the plates are charged and thus produce an E field at all points between them. Assume the field is downward directed, uniform, and has a magnitude of this value. Okay, what is the vertical deflection of the drop at the far edge of the plate? Okay, so the gravitational force of the drop can be neglected. Okay. Okay, so here, so first of all, we would like to calculate the time it takes for the ink to go through this parallel plate. So actually it is like T equals 1.6 centimeter. Okay, so of course centimeter is not an SI unit, so we need to change it back to meter, so it becomes 0.016 meter. Okay, so yeah, in the x-axis it is like a uniform speed, uniform velocity movement. Okay, so it is just like T equals the length over the velocity. Okay, so the velocity or the speed along the x-axis is 18 80 meters per second. Okay, so it actually takes 8.89 times 10 to the negative 4 seconds to go through the parallel plate. Okay, so next we can actually calculate the force acting on the ink or the charge. So F equals QE, so or capital Q. So we have capital Q and also the where is E? E is here. Okay, so actually the Q is 1.5 times 10 to negative 13, and then E is actually 1.4 times 10 to the 6th power. So in such a way, F is 2.1 times 10 to negative 7 Newton. Okay, so actually when we would like to calculate the y-axis displacement, so it is like y equals to 1/2 at squared, okay, according to the high school physics. So we will know this formula, okay, and using the Newton's law of motion, we know that F equals ma, so we have F equals 2mt squared, okay, like this. We try to eliminate a, okay, so with F over m, so we can plug in all the numbers. So actually F is this number, 2.1 times 10 to negative 7, and then 2m, m is actually here, 1.3 times 10 to negative 10, and then times T is this number, 8.99 times 10 to negative 4 all squared. Okay, so actually this one is 6.4 times 10 to negative 4 meter, okay, or you can express it as 0.64 millimeter. Okay, so this is the y-axis movement. So here I would like to supplement the so-called the scientific prefix. Okay, scientific prefix. OK， 那这个的话就是要背一下，就是这些不同时的多少次方是多少。Okay, the scientific prefix is like, so we have a positive exponent like 10 to the third power. 10 to the third power will be k, small k, and then 10 to the sixth power will be capital M. 10 to the ninth power will be capital G. And 10 to the 12th power, of course, it will not be useful. I think it will not be useful in this course, but actually 10 to the 12th power is T. If you are familiar with the computer, the hard disk, you know, okay, the kilo, mega, giga, and tera, okay? Or if you are familiar with GPU, it will talk about T flops. The T is this thing. Familiar with AI, okay, we'll talk about this TOPS per watt, something like that, for the energy efficiency. Okay, so probably you should be able to memorize this C. Okay, so fourth one may not be useful in this course. And for the negative exponent, we will have 10 to the negative 3, which is m, small m, milli. And then 10 to the negative 6 will be micro. 10 to the negative 9 will be nano. 10 to negative 12 will be pico. 10 to negative 15 will be femto. Okay, so this is actually kilo, mega, giga, tera. Okay, and this is milli, micro, and then nano, pico, femto. if you like to write 10 to the negative 18 will be A atto. But this one may not be useful here. So yeah, of course you need to actually remember is the 3 positive exponent and this 5 with a negative exponent. Of course, in between, if you know centimeter, cm 10 to the negative 2 is c, 10 to negative 1 is d. Sometimes we will see dm is actually this thing which is 10 centimeter. Okay, but actually the frequently used scientific prefix are the middle one, are the middle ones. Okay, this thing and this thing. Hope you will remember, because it will be appear in the different problems. Okay, so actually during the quiz or the exams, you cannot ask, oh, what is K, what is M, what is G, or what is small n, what is P. I'll not answer this question. Of course, you can ask some, what is the meaning of a word? Okay, maybe I will answer that thing. But if you ask, what is the value of the scientific prefix, I will not answer. So you should be able to remember, because for engineering students, it will be frequently occurs in different places. So you should be able to remember those things. Okay. Okay, so this is the final part of chapter 22. So it says a dipole in an electric field. A dipole in an electric field. So it means that suppose we have a uniform E field generated by something. Okay, let's say generated by a large charge disk. So it can generate E field in the space. Okay, so we assume that there is an external E field. Okay, so here it says we have an external E field. Okay, and then we try to place an electric dipole of dipole moment P when placed in an external E field is given by a cross product. Okay, so the torque, there will be a torque when we place an electric dipole in an external E field. Okay, of course this E field we assume it to be uniform for simplicity. Okay, so here is the figure to demonstrate this situation. So here we assume we have a E field pointing to the right side, E field pointing to the right side, and this is the dipole. This is the dipole. We assume that we have a Q and negative Q with a distance D, and then it is a fixed structure. So these two charges cannot be moved relatively. Okay, so it must hold like a fixed thing placing there. Okay, so as much as this P and E has an angle larger than 0, then there will be a torque acting on this dipole. Okay, so if we just assume initially this dipole is at rest with an angle theta with this E field, there will be a torque. The idea is like, suppose at the beginning, this is a positive charge and the E field is pointing to the right side, so there will be a force also pointing to the right side acting on this positive charge. Similarly, for this negative charge, the E field pointing to the right side, so the electrostatic force acting on this negative charge will be pointing to the left side. Okay, so here we have this force and this force. Okay, so which means that so here we have a dipole like this, and then we have a dipole like this, and then there is a force acting on this side pointing to this side, and then the force acting on this side is pointing to another side. So in that case, it will be something like this too, rotating. Yeah, if you see it's like pointing, rotating clockwise. Okay, something like this. Okay. So in such a way, it is like, if we try to put this dipole at this position, it will be like this dipole will be rotating clockwise， 就是顺时钟方向。If it is the other way around, if it is like the E field is pointing to the right side and the dipole, I mean Q, negative Q, and then P is something like this. Okay, so in such a way, F is pointing to the right side, this F is pointing to the left side. So in such a way, this is rotating. This is rotating counterclockwise. Okay, so in such a way, this when this dipole is putting in the E field initially at rest, then it will be something like an oscillation. It will be something like, at the beginning, if it's like this, and then it will swinging to this side, and then it stops, and then swinging back. It will going back and forth like this. It will be going back and forth like this. Okay, just like a single pendulum, something like a single pendulum, like this. Okay, just like if you hold the ball like this, and then it will swinging back and forth. So similar for this case. Okay, so the expression of the torque here is tau equals P cross E. This is a cross product. I think you should have learned it in high school physics. And we will talk about this cross product later on when we talk about the magnetism. 就是学磁学28章以后的话，会讲比较多这个 cross product 的。那现在先假设说，就是假设你会了，就是 OK. So actually, for the cross product between two vectors, it is like the magnitude. The magnitude will be the magnitude of P multiplied by the magnitude of E, and then times sine of theta. Okay, so this is the magnitude of tau. Okay, which means that so P and E we assume is a fixed value. Okay, and then here when we see sine of theta, you know, sine of 0 degree is 0. So that's why if this theta is 0, then there will be no force acting on it. Okay, so if it is in this position, there will be no torque, no force acting on it, but there will be some inertial, 就是有惯性啊，所以这个从这边甩到这里来的话，它就会继续往上。那继续往上的时候，其实那个力会往反方向，就让它减速到这个，因为假设说没有阻力的话，它就会晃到这个对称的位置，然后这边就停下来，就会往回，所以它就会一直来回。类似这个的话，就是它会顺时钟转到那个对称的位置，大概是转到这个位置，然后它就会停下来，然后就会换回去，就是来回这样的 oscillation。OK， Okay, so and also the direction for the cross product is like using the right hand rule. Using the right hand rule. For this case, P is pointing to the top right. P is pointing to the top right, and E field is pointing to the right side. So yeah, so using your finger pointing to the top right, and then rotate to the right side. So your thumb will pointing into the page. So which means that yeah, so you can see in this figure it shows that yeah, the free body diagram. So we have a P, and then we cross. Okay, using the finger follow the direction of the small p, and then rotate to E. Your thumb will be pointing into the page. Okay, so which is the direction of the talk. Okay, so if it is the talk is pointing into the page, the rotation direction will be following your finger. Okay, so it's like rotating clockwise, something like this. Okay, so similarly, we have a potential energy U. Potential energy U is associated with the orientation of the dipole moment. So it will also have the potential energy, something similar to the pendulum. So yeah, so the potential energy will be negative P dot E. So yeah, for the dot product, the magnitude will be the product of the magnitude of P, and then multiply with the E. So PE times the cosine of theta, and then with a negative sign. So in such a way, when theta is 0 degree, cosine of theta is 1, which is the maximum value, but after taking the negative sign, so U is minimized, which means that at this point, or when P is pointing to the right side, the U is minimized. Okay, U is minimized. Okay, so when theta is 180 degree, cosine of theta is -1. In such a way, U is maximized. This is negative Q, and negative Q. Okay. E is pointing to the right side. Okay, in such a way. So this is the extreme case, which is like
就是它这边是正的，这边是负的，那它就会这样晃一圈，然后再回去。那但你假设说它如果是179.9度这样的话，它往上偏一点的话，它就会转大半圈，转到差不多的位置，它就会放回来，它是最激烈的状态。
Okay. So this is about the torque and the potential energy when we put the dipole in an uniform electric field. Okay, so finally we have two additional examples. So let's finish quickly. So here it says a clock face has a negative point charge, negative Q, negative 2Q, all the way up to negative 12Q, fixed at the position of the corresponding numerals. 所以就是像一个时钟嘛。No. No. Okay, something like this. Okay, we have a circle, and then we have a charge, a negative Q, negative 2Q, negative 3Q. all the way up to negative 12Q， 就是时钟嘛，就是1点、2点、3点，就每1点的话就有 negative Q 啊，7点的话就有 negative 7Q 这样 ，OK。然后the clock hands do not disturb the net field due to the point charge. At what time does the hour hand point at the same direction as the electric field? OK， 所以我们现在有12个电荷，就是负 Q 到负12Q， 然后在这个圆上面了。然后他问你这个中间这个圆性的位置，它的电场啊，它的电场是指向哪一个方向呢 ？OK， okay, so actually we can make use of the symmetry. So the hint is using the symmetry. Okay, so actually for the negative Q and negative 7Q, so Q and negative 7Q can be party cancel. So it remains negative 6Q. Okay, when we consider the E field, so which means that the negative Q will generate a small E field pointing to the top right, and negative 7Q will generate a large E field pointing to the bottom left. Okay, so party cancel. Okay, so it becomes something like negative 7Q remain, and then we remove that one. Okay, so it will be equivalent. And similarly, if we have a negative 2Q and negative 8Q, similar thing will happen. So it remains negative 6Q at the 8 o'clock position. So on and so forth, all the way up to negative 12 and negative 6Q. So we will have mainly negative 6Q at 7 o'clock, 8 o'clock, 9 o'clock, 10 o'clock, 11 o'clock, and 12 o'clock direction. Something like this. So in such a way, adding all this vector together, the total E field will be pointing to this direction. Okay, so which is actually 930. Okay. So this is the answer to this additional example. So let's go to the final one. So it says, suppose you design an apparatus, 就是一个装置啦, in which a uniformly charged disk of a radius r to produce an electric field. The field magnitude is most important along the central perpendicular axis of the disk. Okay, so and then at point P at a distance 2 out from the disk. Okay, so we will consider the E field generate at point P, and this point has 2 out distance from the disk. Okay, so cost analysis suggests that you switch to a ring of the same outer radius r, but with inner radius r over 2. Okay, 所以这个 case 的话，就是这个半径是 r， 那这边的话半径还是外面的半径还是 r， 但是里面的半径是 r 除以2 r over 2. So assume that the ring will have the same surface charge density as the original disk. Okay, if you switch the ring, by what percentage you will decrease the electric field magnitude at point P? OK， 所以这个意思是我们有电荷在上面均匀分布的，然后我们挖掉中间的部分，然后挖完之后那个电荷密度不改变，那所以总的电荷是变少的，所以他就问你那个 E field 在 point P 的话减少多少 ？OK， so we will make use of the equation E equals sigma over 2 epsilon naught 1 minus z over z square plus capital R square. This one. Okay, so this is the E field generated by a disk, and we assume this is not infinitely large. Okay. So actually, we assume this is A, this is B. So for EA, it will be sigma over 2 epsilon naught, and then 1 minus this Z For this case, z is 2r. So we have 2r and then 2r quantity square plus r square, and then take the square root like this. Okay, so this is our sigma over 2 epsilon naught, 1 minus 2 over. Okay, we'll finish quickly. Okay. So for the EB, it will be something like sigma over. Okay, so we consider the middle part will be B. The middle part will be B. So we have a sigma over 2 epsilon naught. So we have 1 minus 2r over 2r quantity square plus r over 2 square. Something like this, which means that we remove the middle part. Okay, so we try to subtract this part out. So actually this part is sigma over 2 epsilon naught, and then 1 minus 4 over square root of 7. Okay, so finally we would like to calculate the E hollow, 就是空心的那个盘子除以 EA 的话是 actually is like sigma over 2 epsilon naught or over sigma over 2 epsilon naught, and then we have 1 minus 4 over square root of 7, and then here we also have 1 over 2 over square root of 5. So we have 28.3% for this additional example. Okay, so here we'll